So, hello once again for this second round of talks with various quantum engineers from around the world. If you've joined us again for this chat, thank you, considering it's only been 5 hours since our last one with Jeremy O'Brien. So for our second chat, I'd like to welcome Dr. Austin Fowler, who I've worked with for quite a long time. He is now, I think your title is Quantum Electronics Engineer.
That's correct.
Now working at Google in Santa Barbara, California. So Austin, thanks for joining us.
Always a pleasure.
So first off, basically just give us a bit of a rundown. I mean, obviously I know your career quite well, but basically how you ended up at Google and what specifically do you work on?
Sure. So I ended up in Google by chance, largely, to be honest. So I was working in Melbourne with IARPA, which is one of the US government agencies. They were funding essentially software research at the time. And when that ended, I joined up with John Martinez, who was working on hardware, because I really wanted to see the theoretical work that I'd been doing for most of the decade before that put into practice, put into real hardware. And I felt John Martinez had the best chance of being able to do that. And even that transition was a long process. It took possibly a couple of years of on-off conversation to actually make that happen. But when I finally did make that transition, it was a chance to actually see error correction put into real circuits, see real errors in real hardware detected and then processed with the software that I've been writing for a long time. So that culminated in some experimental work that we did, repetitive error detection, where we were able to show for the first time detection and correction of bit flip errors. So it's still an essentially classical error correction code, however, done with quantum hardware. So showing that the quantum hardware was good enough to actually correct its own bit flip errors. So we're not there yet. We still have more work to go. During the production of those devices and the processing of that experimental data, we were in our own transition away from IARPA. So John was also funded by IARPA at the time and looking for other ways to keep the group going. And we ended, or I should give full credit to John on, in this instance, to actually talk to Google, because Google has had its own interest in superconducting quantum electronics for a long time through dwave, and was interested in having an experimental arm to physically investigate different ways of doing things with superconducting circuits. Something
So
that John was.
I'm sorry. I suppose that's the thing is we should probably say what your technology actually is, because we had linear optics a bit earlier, and
That's
so you're
right.
working on
So
superconducting systems.
Circuits. So solid state chips with superconducting traces with breaks in them that give them special nonlinear properties that allow you to support quantum bits, qubits. So in our case right now, you're basically looking at a sapphire wafer coated on the top with aluminum if you're in the US, and then you cut lines and gaps in that layer to define your actual circuits and put on a few more layers with oxide in between them to define all of the Josephson junctions. So if you have aluminum oxide, another layer of aluminum, you get what's called a Josephson junction, which gives you something nonlinear, and that nonlinearity allows you to build, to keep a long story short, essentially a qubit. It gives you a potential landscape for one of the variables associated with this superconducting system that is sufficiently well controlled that at the bottom of those potential wells you get quantization of energy levels, and we can use the ground and first excited state to be our zeros and ones. And then using microwaves and magnetic fields, we can modify this potential landscape, drive transitions between the ground and first excited state, and execute our gates. So yeah, you're looking at a chip at the bottom of a dilution refrigerator. We operate as close to 10 millikelvin as we can. A whole bunch of, at the moment, coaxial lines that run from the cold sample to room temperature electronics. And now it's our job to get this higher fidelity and cheaper. So one day all of those electronics have to be put in the fridge, but for the moment the focus is squarely on fidelity of operation. The number one reason why today we don't have really quantum computers at all, at least of the kind that we work on primarily, is the fidelity of the components. It's just not high enough yet. We've spent 20 years working on getting them better, but it still needs to be a little bit better still before you can say, here are the components I need. Let's just build our quantum computer. So we feel we need to decrease error rates, particularly the error rate of the 2-qubit interaction. If we can decrease that by a factor of 3 or 4, that should be good enough. And then we can really say error correction is possible. Because in addition to the bit flips, we have to correct phase flips. And we also have to correct leakage. And we just need a little bit more room in our error budget to be able to handle those 2 additional error effects.
So I mean, your development has been very, very heavily on architectures and specifically error correction. And this does relate into meQuanics itself and what we're trying to do with that. So is it possible to explain within a minute or two is to essentially what a quantum computer is? Because it is an error correcting machine, isn't it?
Sure, absolutely. And that's absolutely correct, that the software that runs the hardware that we built here is very strongly tied to meQuanics. So if you imagine a 2D array of quantum bits, and for visualization purposes, just imagine every quantum bit as a little plus sign. It's basically a capacitor, that little plus sign. And when you have an array of these little plus signs, everywhere they're close to one another, that defines an always-on interaction. So that's our fundamental hardware. Essentially a whole bunch of capacitors. They're connected to tunable inductors. That gives you a tunable resonator. So you can tune the frequency of these qubits, and when you want them to interact, you bring them into resonance. When you don't want them to interact, you take them into a pair of different frequencies so that they don't talk to each other. So crudely speaking, that's all our hardware is, a whole bunch of nonlinear oscillators that can be driven between their energy levels and brought into resonance so they interact. What you then need to do is error correction. So if you imagine any one of these little plus signs, it talks to its 4 nearest neighbors, 4 arms of the plus sign, and you can use any one of those qubits to detect errors in its 4 neighbors. And you then end up with this checkerboard pattern of qubits that use for error detection, qubits that use for data storage, and that alone is just enough to store information. If you want to do computation, what you start doing is turning off rectangles of qubits that then become 2 patches of qubits, and then you leave those patches off. And what, if you can imagine, that defines is essentially a U shape in space and time, where you've initially turned off a patch to prepare a protected piece of data, and then kept the 2 ends of it to create a U shape. And that location in your hardware and software defines a protected piece of quantum information. Where meQuanics comes in is, well, one isolated piece of protected information does not a computation make. You have many of these. And then when they start twisting and braiding and connecting and joining and being capped with other U-shapes, this is really what the computation looks like in space and time. And of course, for meQuanics, the idea is to keep that picture so that anyone playing meQuanics is really genuinely reducing the space and time overhead of the computation without then burdening the player with all of the details that then go behind that. So, it's a great opportunity to take an interesting quantum computation that has been expressed in a fault-tolerant, robust manner as this complicated 3D tangle of pathways. We typically call them defects. So all of these tangle of defects defines our computation, and then just start compressing. It's something we actually do need very badly to bring down the overhead. So I'm certainly, for one, very optimistic that this approach can be a powerful way to bring quantum computers a bit closer.
So you've been an advocate of these models of computation for quite a long time. In your mind, they're the best that currently exist, and the
in my
best
mind,
that
they're
ever
the
will
best that
exist.
ever will exist. Yeah, for a lot of reasons. At least in my mind, our particular hardware approach has the best chance of achieving a universal set of high-fidelity gates. That's not to say other approaches haven't achieved higher individual gates, higher fidelities, but it all has to be put together in one system. And at the moment, at least in my mind, we hold the record for the highest fidelity universal set of gates, all in one system, and with a relatively large number of qubits, so 9 qubits at this point in time. Many other approaches really do struggle as you add more qubits to the system, and as you try to do every possible gate in one system to maintain high fidelity operation. Despite that, the fidelities even we can achieve are not high enough to do any form of error correction whatsoever at the moment. Apart from the one caveat that I mentioned is, just one type of errors. The easiest to correct class of errors we can correct, but not the 2 other classes of errors that I mentioned. So you really then have to search for what type of error correction is going to be nearest term implementable. And at the moment, that's the surface code. And it's the surface code for a number of reasons. The surface code only requires a 2D array of qubits, which is what we're building. It only requires nearest neighbor interactions, which is great because that's all we're going to have. And it requires error rates below about 1%. So, you want to shoot for about 0.1%. So you're well below the threshold where this thing works. Currently, our hardware sits right on threshold. So, a few gates are above 1% error, some are below 1% error, and it's just enough if you squint and squeeze in the right way to correct bit flip errors, but not enough for phase flip and leakage. And as I mentioned, if we can get a factor of 3 or 4 lower error, then we should be good for all types.
Now, these models are distinct from what some people may have heard of as topological quantum computation. I mean, we sometimes refer to these as topological codes rather than topological computation.
Yeah, topological quantum error correction is what I would term the surface code. So yes, there are 2 types of research in our field that start with topological and end with different words and are very different. So topological quantum error correction is where you are really actively trying to detect errors and then using software to correct them. And that's the approach we favor. The other approach, topological quantum computation, you are really trying to use physics to create particles that by their very nature are robust against errors. This is a very different approach. It requires very different hardware to what we're looking at. There's, always some controversy in terms of that particular approach as to whether the necessary particles that are supposed to be rust have been observed or not. I'm not enormously optimistic about that approach, but I'm glad that people are looking at it. It's still a long way before topological quantum computation has a universal set of gates with high fidelity. So that's really, for me, where things start getting interesting, when you actually have gates and can do computations, actually check how robust the gates are. And it still seems that's a long way away in topological quantum computation.
So Google has recently come into this space, obviously through the lab that you work with and through another lab that operates one of the dwave machines. So this has started moving more into the private sector. There are other companies such as IBM that are also looking at this. Do companies like this really, is it now shifting away from academia and into the private sector with places like Google, IBM, and there's a few other startups that have also come into the field?
Yeah, I mean, the short answer is, in my case, I certainly hope so. Clearly, I've made the transition from academia to industry. In my opinion, most of the theories that we have needed to build a quantum computer are in place. And at least in any experimental lab, the vast majority of what needs to be done is known. That's not to say it's easy. It's not to say we have the answers, but the types of investigations that need to be done are known. So when that's true, it becomes less and less academic when you're actually researching. The work you do becomes less and less academic. The work I'm currently doing would not easily fit into the academic model. So at the moment, my day-to-day is programming faster versions of error correction. In academia, that would be a project I would avoid doing because it takes a very long time. And even when it's complete, it will be a new version of software that does exactly what the old version did, just faster. And it may take me as much as 2 years to complete that project. So I feel I'm about 1 year in, maybe halfway through, hopefully. But it may easily take another year for me to finish that. Now, in academia, that would be very bad for my career to do a project like that. And there are many similar projects that need to be done if we're going to have a quantum computer. In my case, if I don't do this project, there will not be software that can keep pace with the quantum computer. End of story. You can't build a quantum computer. So I have to do this work. I need an industry sponsor that can say, oh, okay, we need that. You should do that. And that's it. That's as far as I need to go to justify that project. Not where will it be published? How many citations will it get? How many conference invites will I get? That's no longer the consideration, and it can't be. I have other colleagues who are tasked with improving the fabrication process. So literally the recipe, what temperature, what chemicals do you use to clean, what duration of ion beam milling, and all of these little technical details. And again, in academia, that would not be a great thing to be doing. If you're looking at the geometry of the qubit, exactly what width of everything does it need to be, and so on. Better wiring, better ways of writing the control software. Many projects are done in our own group that really would be very difficult to do in academia. Now, we certainly try to support people in academia that do projects of this nature. So we do encourage people to do that. We encourage people to share the fruits of such labor, which are then often practical pieces of technology or techniques that can be used in other labs. Wherever we can, we try to actually support the publication of works done in that manner. But it is harder to do.
So you think a cusp has been reached where this will flow in and actually become the next technological revolution?
I think there's certainly beginning to be a split between academic style research, which is more, and always was intended to be, generation of ideas, and then industrial style research, which again has always more, never exclusively, but more so the development of ideas. And we'll see how far that split grows over the next couple of years. It is expensive and difficult to have many qubits in one system, all being controlled in a manageable manner. There's just a lot of hardware you need to build, a lot of software you need to write. I'm not saying it can't be done in academia, but it strikes me as increasingly inappropriate for academic research as time goes by. Time will tell, but that's my feeling as to what will happen.
Right. So in terms, people have been reading a lot of high-profile newspaper articles and various things like that about the applications for quantum computers. Now, I know you have very specific thoughts on that as to maybe what they can be used for and what they probably can't be used for, at least in sort of the medium term.
Sure. So medium term, long term, and if we start with long term, my personal greatest hope long term is chemistry, so quantum chemistry and its related technology. It seems to be the area where we have the best chance of cracking interesting problems, so commercially interesting problems. nothing's guaranteed, but at the moment there's a lot of development in that area, a lot of people writing a lot of exciting algorithms in that area. The overheads are still not small, but they're smaller than many of the other computer science style problems that have been thought up to date. But we have a long road to get there. So along the way, number one, the biggest milestone we need to hit, and the sooner the better, is just showing that quantum computing is possible in principle, have a system that really is correcting all of its errors, is scalable, can in principle support computation. So that, we would love to be able to get there within 2 or 3 years. Well, the less, the better, but, we would really like to hit that milestone. And because then things change a lot. It no longer becomes a case of can we build a quantum computer? It becomes a case of can we build this computer cheaper, faster, better? It will work. We need to make it economic. That's where we really hope to see a lot more people get involved in quantum computing. Once that speculative aspect of quantum computing is removed, and you can go to an engineer and say, okay, we have 100 wires coming into our fridge. We need 10,000. And if we do it in the naive wave, it won't work. Can you think of a creative solution to this? We have 50 channels. We need 50,000, right? And really try to get engineering style people really focused on scaling things up. So yeah, it's a case of getting to that point and as quickly as possible. And once that happens, once we are convinced a quantum computer can be built, it's an engineering challenge only. So no theoretical challenges, just an engineering challenge only. Then I really hope that might excite a lot more interest from people that spend their days writing algorithms, classical algorithms, to get interested in quantum algorithms, and hopefully really open up the field in terms of potential applications for a quantum computer.
So yeah,
my personal belief, is
sorry.
we're not going to get the very best algorithms for a quantum computer until people that are very clever and spend their life working on algorithms can justify the time to actually learn about quantum computing.
Do you think that they need a device to play with, or do you think that paper and pen is sufficient?
I think they need a device to exist to provide motivation. I don't necessarily think that you need a quantum computer to do research into quantum algorithms. We have a number of quite well-developed simulators, and for many purposes, that's enough. It's enough to learn about quantum computing, to test a few small algorithms. To design a quantum algorithm, I don't think it's the hardware you need, it's the understanding you need. And it just takes time. So to provide a quantum computer that could outperform a classical simulation of a quantum computer will take quite a while. This is not a work of 2 or 3 years, because you're talking about building a quantum device that has more than 40 qubits, because if you try hard, you can simulate 40 qubits classically. More than that, if you try hard, you can simulate 40 qubits classically exactly with no errors. So you'd be talking 40 logical qubits with heavy error correction. We're talking tens of thousands of physical qubits here to do something similar. That's a big ask. And even then, it would still only be comparable to an expensive classical simulation. You need possibly hundreds of thousands before you're doing truly quantum computations that you just cannot do classically.
Right.
And even then, with such a computer, by definition, if it's something you can't do classically, it's not obvious the extent to which that would help you write a quantum algorithm. It may be enough just to understand how quantum circuits work and work with them on pen and paper. That's how they've been created to date.
And I mean, people should be aware that there's a lot more algorithms than just factoring.
There are indeed. In fact, there's a quantum algorithm zoo online, which has some 100+ different algorithms. as I say, the biggest field that I think people should be aware of is the whole quantum chemistry aspect, where there are a number of interesting algorithms, more out all the time. People are optimizing them rapidly, and these have a lot of potential industrial applications. No one's saying it's easy, but it seems possible.
So one thing to make a distinction, especially for people who are smart and capable but are not trained in quantum physics, is this division between the hardware and the software. Because the software, you don't need that much training, at least the software required to run the kind of quantum computers you guys are trying to build. Not so much programming them and quantum algorithms, but the other stuff.
Sure. It's a tricky problem. I mean, yes, that's true at a certain level. So to take a quantum computer simulator and run a bunch of CNOT gates and Hadamard gates, that doesn't require that much training. The goal, of course, of our group is to make sure that you don't need much more training than that. But to actually build a quantum computer right now, I can tell you for a fact there's a lot of very hard software that needs to be written, because those relatively simple gates then need to be decomposed into thousands and millions of physical gates, and they need to be arranged in a very careful way, and you need to do all sorts of measurements during the computation that feed forward and determine what gates you need to do next, and it's actually very, very complicated. Now, that's of course not necessarily something we expect to get help with, but it should be very clear that building a quantum computer right now, at least in our lab, is at least equal parts software and hardware. The complexity. And that's in a largely hardware-focused lab where there's at least half the people that spend a lot of their time doing software, including some people that are full-time on software. So, we certainly do need programmers. One thing we're always in search of is very good programmers that are willing to learn the necessary, relatively small amount of quantum mechanics to then help us actually build a computer. So that's essentially the sphere of research that I work in. Relatively small amount of quantum mechanics knowledge, but very heavily focused on software. Certainly one day, we hope to provide tools where you only need a small amount of programming, and away you go, you don't need any quantum mechanics, but that's not true in our lab right now.
So in terms of what you're allowed to speak on, where is the hardware heading in Google's labs in the next 2, 5, 10 years?
Sure. And Google is still very open at this stage of development. We fully recognize that getting a quantum computer built is still very much a world collaboration rather than this one lab is going to do it on their own. That's not our attitude. It's why we still go to conferences, we still present at conferences, we still very much invite people to come and visit and talk. So, it's not as though we operate in any way secretively at this point in time. So with that fully clear, I mean, there are a number of things that we work on. We do work on dwave style annealer technology. That is part of what we do. We also work on the technology I've been focusing more on in this talk, this 2D array of X-shaped qubits, call them XMONs. There's also a third branch of the technology where instead of just directly coupling these X-shaped qubits, we have a tunable coupler between them, which spreads the hardware components apart a bit further and gives you a tunable strength and sign interaction, which can be useful for other things such as quantum simulation. So those are the three main types of technology that are being worked on. And in all three cases, the goal is a large-scale 2D layout. So, we have a clean and clear picture for those pieces of technology. All three approaches use essentially the same fridges and wiring and control electronics and control software. There's a lot of common ground in terms of the fabrication and all the support equipment for all those three approaches. And then each little mini project has its own leads that then work on those different approaches. But largely it's about making everything required to build quantum hardware better. So for a long time, for example, we had wire bonds from our chip samples to the sample box, then would go to coax lines and out to our room temperature electronics. So we're looking to replace those with bump bonds, which we hope will support far more connections, better quality connections, a better 2D layout with essentially 3D wiring. And that's just one example of many, replacing standard SMA, which just means big really in this case, coax cables with finer and finer cables with finer and finer connections, getting them to put into assemblies, engaging external companies to do that. And every aspect of the technology that we can make better, getting everything that's a monolithic macroscopic piece of hardware, trying to put it on a circuit board, get it working at low temperatures. So, you know, most of what the lab does is working on the support technology of quantum computing, because most of what a quantum computer is not that little chip right at the base of the fridge. It's everything else that takes so much work. Everything takes work, but you know, the control software alone, the control electronics alone, chew up a good third of the lab, keeps them busy. The wiring, the fridges, all the electronics at the bottom, I mean, you know, that's probably another good third. And then the remaining third are focused on those 3 different types of technology. So annealers, the 2D array of XMONs, the GMONs. So all of those people are probably just 1/3 of the lab. The rest is everything that supports those projects.
So what is the distinction between the D-Wave annealer or the annealer you guys are developing and the kind of full-blown universal quantum computer that you're more focused on?
Sure. There are really many more differences than there are similarities. So if we start with an annealer, we need to essentially have an easy to prepare initial state. So something which you can just get by allowing the quantum bits, the qubits, just to settle to their natural state. So an easy to prepare initial state. And then a bunch of interactions between those qubits whose ground state is the solution to some interesting problem. So the lowest energy state that is consistent with all of those interactions should be the solution to an interesting problem. The key then is to move the system from the easy to prepare initial state to the hard to find ground state solution in just the right manner. Generally speaking, slowly, but it can be more complicated than that. In just the right manner so that you don't disturb the computation and fail to get the answer you want. So that, and those few words encompass a lot of research. Exactly how you encode your problem in hardware, a lot of research. How you get from the initial state to the final state, a lot of research. Which problems you choose to try to encode it all, a lot of research. But essentially the goal is don't use any error correction. Build hardware that is as close as possible to the problems you're trying to solve. Use quantum mechanics in the most efficient manner to just solve problems that can be solved quickly. So the current hardware is not universal in the sense that any possible problem under the sun can be encoded in this manner. But people believe there's a wide range of interesting problems that can be solved, maybe, using this approach.
So they're much more problem specific and they're trying to get away without using error correction.
That's correct. So it's a more limited class of problems that even have the potential to be solved. No error corrections. The hope is that there is a much lower hardware overhead and therefore the computer can be realized sooner. So the other approach is very different. So what I do, it's all about error correction. It's all about reaching a performance level where you can correct errors. So when you do error correction, that immediately implies significant hardware overhead. There's no getting away from that. What you get for your significant hardware overhead is, in principle, arbitrarily low error rates. And then, at least on paper, you can perform whatever computation you want, taking however long you want, and get your solution to any problem you can imagine. So you really have to choose your poison. Do you take the engineering approach, the hopefully short-term approach, no error correction, build everything the best you can and hope that it's good enough and your system is big enough to solve interesting problems? Or do you take a little bit more of a long-term view and say, right, now we want to be able to solve any problem and we want to be able to do it reliably and be sure that the answer we get is what we want. And then you need the overhead of error correction. And then there is a third approach, which I mentioned we do look at as well, which is quantum simulation, where you really focus on the tunability of the interactions between your qubits and encoding interesting physics into the system and seeing, again, if you can simulate interesting physics using controllable hardware. So, yeah, I would say we study three distinct approaches.
Mm-hmm.
Simulation, where you're trying to sort of build a physical analog of the physical system that's just more controlled. Annealing, where you're trying to use the minimum amount of hardware to encode a problem and hope your hardware is good enough to get the solution without error correction. And then finally, full-blown error-corrected quantum computing, where the hardware overhead is more challenged to hit, but it's a fully general computer. You can do anything once you've got it.
Yep. So basically, your interest is more for certainly the longer term and try and get it done properly.
Yeah. That's my personal belief. That is what we need to do to have a real computer. Mm-hmm. Just my personal belief. We still certainly cover other bases, and my personal belief comes from what happened in classical technology, where for a while there were analog computers, and then eventually it just became cheaper if you wanted an analog variable just to have a register with 64 bits and emulate a continuous variable using bits that were error corrected and reliable and robust. That's also my feeling with the digital technology, the error corrected technology that we work on, that it may well prove that if you want an annealer, you actually go and use digital technology, error corrected technology, to emulate the annealer, emulate a quantum simulation, break it up into discrete gates, error correct them, so you have a better chance of doing a large-scale problem, still getting sense out at the end, and getting an answer you care about with high reliability.
Wonderful. So we're just coming up just beyond 30 minutes, so I think we might bring it to a close in a second. But one last question is, so Jeremy earlier on in the day talked about what could be doable by 2020 from the perspective of his lab. Where do you think Google's lab could stand by the end of this decade?
And the number one thing I hope that we have by 2020, so 4 years-ish, is I really want a convincing demonstration that large-scale quantum computation is possible. I want to really have a very good system, perhaps 100 qubits plus, which is operating with sufficiently low error rates to say, right, it works, it corrects all of its errors. We have a clear pathway to scalability. We have a good and reasonable price per qubit, and then we have a good handle on all the bits and pieces that need to get cheaper. So, a clear picture, technology that works, and a clear pathway forward. That's really all I hope for, and I hope will be more than enough and exciting by 2020. I'm not so hopeful that we can do much more than that. And of course, we're always trying to push things as quickly as we can, but I'm hesitant to promise an enormous computer that can solve classically intractable problems in 4 years, given we can't yet build a computer at all. So I think it's most realistic just to say that we want to prove that quantum computing is possible.
Well, the digital computer didn't happen overnight.
No.
Well, I think we'll call this one to a close. So thank you very much, Austin, for taking the time out and having a chat in order to keep promoting meQuanics during our Kickstarter campaign. And for those of you who want to donate, and I please encourage you to do, because we'd like to continue building up the game and hopefully getting the public involved in helping Austin and many of us out and trying to program these things. So there is a link to the Kickstarter underneath this video, and please donate if you have the time and the money. So this series will continue for the next 3 weeks and may even continue beyond that if we get some good response. I still have to line up the next interview. Not sure who it's going to be yet, but either keep logging onto our Kickstarter page or our Twitter account, and I will update you when the next one is scheduled, hopefully early next week. So thank those of you who joined us, and thank you again, Austin. Cheers.